All right, hello everyone. It's Dr. Horrod here again. I'm just going to spend a few minutes giving you an introduction to what you'll be doing next week in the lectures with Dr. Yusuf and how it relates to physiology and actually probably more neuroscience. So next week you'll be doing light and optics and how that relates to vision. And the first thing to first know is that light is both a particle and also a wave. So just be aware of that as I'm talking to you now. I'm sure Dr. Yusuf will go into it in a lot more detail next week, but you just need to know that. Now, when you look at someone or something, that thing isn't actually emitting light, I guess, unless it's a lamp or something, but it isn't actually emitting light. So if you're looking at a person, so let's have a look. Here's this person here. As you can see, I'm not too good at drawing people, but here is this person here. What you actually see is reflected from the sunlight. So the sunlight shines down, the light comes down, hits that person, and then it reflects. And what you see, here's you over here, looking at that person, that's your eye. What you see is the light particles or waves being reflected off that person, and that is what you actually see. Now, how we see, how we get from the information going from the person into our eye and then processing it into actually being something we see is very interesting. But we can't really talk about this yet because what we need to look at is something called refraction. Now, I'm not sure if you've heard about refraction before, but what happens to refraction is when light waves are bent, or the light ray, I guess it's more correct, is bent. So let's just have a think of a situation where this might occur. Again, we've got a person here, and they're standing in some water. Here's the water here. And they're standing on a big rock, so it's deep water. So they're standing there and they're looking into the water. And they're looking through, looking down, looking down, looking down. And what they see here is a fish. There you go. It's a very happy fish swimming in the water. Now, when they're looking from up here and looking down, it looks like the fish is here because it's a straight line of view. But what actually happens is here, of course, you've got air, and here you've got water. Now, the speed at which the light ray travels is different in air and water. It's much faster in air than water. So when you're in different mediums, light or the speed of the light ray will change. And when the speed of the light ray changes, at the actual boundary between the two mediums, it will bend. So what actually happens is that when you're looking here, light ray is bending. And so if the medium, water, slows the light ray, it will actually bend the light ray towards normal. And so the fish itself is actually here. So this is where the fish actually is. When you're looking, you think the fish is here. But actually, the fish that you're looking at is sitting here. So light is reflecting off that fish, it's going here, and then when it enters the air, so at the water-air interface, because air speeds up the light now bends away from the normal. See that? And so then you can see it there. So that's refraction, and this purpose, or the reason why I talk about refraction, because this is almost pure physics obviously, is that your eye, or the process of you seeing something, depends upon you being able to refract the light coming into the eye. And this is very, very important, all right? So this is how our vision works, all right? So let's have a look now. I'll do a really bad picture of an eye. So here we go. And I'm just doing the important parts of the eye. All right, so we've got the outside here, which is the cornea, which is transparent. That's the first place of your eye where light actually enters the eye. You then have the lens, which I'm sure you've all heard about. And at the back of the eye, we have what's called the retina. Now, what happens in vision, I might even change the colour here. What happens in vision is that you need to produce an image on the retina of what you're actually seeing. Now, the way that this is done is, let's have a look. Let's make someone here again. Let's make a person. Oh, yeah, let's make a person. Okay. So a person is standing here. Now, the light is reflecting off them. Let's look at the top of their head first. So the light is reflecting off the top of their head, and it travels to the cornea. Now, the cornea, or inside the cornea, it's sort of thick type of medium, I guess you'd call it. It's sort of a tissue. So therefore, it's a different type of medium than outside, which is air. So we have air here, and then we have the medium, which is forming the cornea. So therefore, the interface between the two is going to cause refraction. Refraction is going to be caused. And because the cornea, or within the cornea, the light ray is slowed, it actually bends the light ray closer to the normal. Okay, so the cornea is curved, so that means the normal's at an angle. The light ray comes in, and then we bend it closer to the normal, and then it hits, the light ray hits the retina here after passing through the lens. Now, of course, the light doesn't just go from one point to one point. There's a whole series of points. So if the ray hits the cornea at the normal, so the angle is the same as the normal, no refraction takes place, and it goes straight on here. Now, in order to see a focused image, what happens is these rays, different rays coming from the same area, have to be hitting the retina at the same point. So if, for example, the retina was, let's move the retina for a minute, if the retina was here, you'd see that the same point is showing here and here. So if the retina was here, you'd see a whole different group of signals. You'd have a whole different group of signals showing the top of the head is in different places, and this would produce a fuzzy type vision. So how do you make sure that you're focusing on the retina here, on this point here? And I'll go back to red. Well, the reason why you can is because not only do you refract here at the cornea, there is also some refraction occurring at the lens. And what the lens can do, and the lens is quite interesting, here's our lens. What our lens can do is it can change its shape. So the lens can be bulgy, or the lens can be very thin. And so therefore the angle that the light hits, here's the normal there, here's the normal here, can be changed by the shape of the lens. So you have the ability to change this. You can actually change the shape of your lens to make sure that the bending of the light rays coming in are focused on the back of the retina. Now, of course, Dr. Yusuf will go into this in a lot more detail, and also you'll discuss it in your neuroscience lectures as well. So you can see that in order to get an image on the back of your eye, you need to first refract at the cornea. And this is where most of the refraction occurs. And then you can fine tune it by adjusting the shape of the lens. And your body does that. Your eye does that, automatically. and this is called accommodation. And you'll look at accommodation when you do neuroscience. Okay, so just to finalise here, because we've really only looked at the top of the head, so let's go back and let's this time do it in green. Let's look at the bottom of the toe, okay, or this one here. So again, the information comes here, hits the cornea. Again, here's the normal. So we get refraction. Sorry, hits the cornea here. Get refraction, it bends in, and the information goes there. If it hits the cornea at its angle, so it's hitting it perpendicular, passes straight through, and it crosses there as well too. So the symbol or the image that you get on the back of the retina is actually an upside down one, and you'll discuss this a lot in physics, and you'll probably most likely do it. Yeah, you'll just definitely discuss it in physics and discuss it in neuroscience as well too. So what we have now is when we look at the person, we refract the light, the lens fine-tunes it so it's focused, and then what we have here, here's our retina, is an image of the person upside down. Now obviously, when we look at someone standing up straight, it isn't upside down to us, and that's because we have receptors that send all this information of that image, travel through what's called the optic nerve, and it goes to the visual areas of the brain. And what the visual areas of the brain do is process that information, send it to our mind or our perception areas, and what we see is we see the person standing up straight. The image that we see here and here will be the same. Okay, so to summarise, what you'll be learning about in physics this coming week is you'll be learning about what light actually is, that it's a particle and a wave. You'll be learning about refraction. You'll be learning about how light rays are bent through different mediums. So you'll look at that. You'll look at reflections as well too. And you'll be then, as the week goes on, you'll then look at what happens in the eye. And Dr. Yusuf will go into a lot more detail about what I've talked about here. The fact that the light rays first enter the eye via the cornea. That's where you have the greatest refraction occurring because of the change in medium. And so most of the light is bent at the cornea. And then when the light enters the lens will fine tune to make sure that your image is focused. So the lens gives you the ability to look at a faraway object and focus, and then look at a close object and focus as well too. This information that you get of the image that's produced, the upside down image that's produced on your retina, is converted by photoreceptors. Information sent through the optic nerve to the visual areas, where you then perceive the image of the person standing in front of you. Okay, I hope this helps give you a bit of an understanding of why you'll be looking at light rays next week. Thank you.